Now that we know what forces are and what forces can do, we need to look at what happens to objects when more than one force is acting on it. So on Earth, objects usually have many forces acting on them. These forces can act in many different directions. An example of this could be tug of war, where two teams are pulling on a rope, but they are pulling in opposite directions. In this case, let's say that the team on the left is pulling with a force of 1,000 newtons on the rope, and their force is being directed towards the left. Let's say that the team on the right is also pulling with a force of 1,000 newtons, the only difference being the direction of their force is towards the right. Now you probably know from experience in this case, with two teams pulling in opposite directions with the same amount of force, that the rope is not going to actually move, which means that both teams, because they are connected to the rope, are also not going to move. So we know that both teams are pulling with the same magnitude, which is a word that means an amount or a size. They're both pulling with the same magnitude of force, which is 1,000 newtons. We also know that each team is pulling in the opposite direction, one to the left and one to the right. So we need to calculate what we call the net force, and net force is the overall total force that is acting not only just on the rope but on the teams themselves, and we treat them as one object in this case. So we need to add the two forces that are being applied, 1,000 newtons to the left and 1,000 newtons to the right. Now what is really important in these calculations is that we take these two directions into account. If we didn't take the left and right directions into account, we would just say that the net force equals 1,000 newtons plus 1,000 newtons, which would give us an answer of 2,000 newtons. However, when we're talking about forces, the direction is critical. Because these two directions of these two forces are opposite, the action of one force is being counteracted or balanced by the action of the second force. So in some ways they are cancelling each other out, and that gives us a net force of 0 newtons. And because the net force is 0 newtons and both teams started from a stationary position, both teams' motion will be unchanged, which means they will remain stationary. Let's look at a different example. Here we have a set of scales, and what we can do with that set of scales is we can put a 1 kilogram mass onto one side of those scales, and we know that because gravity is acting on the mass, there'll be a force of approximately 10 newtons downwards due to that 1 kilogram mass. Now we would look at that scale and say it is unbalanced because there is more mass on one side of the balance than the other, and you'd be correct, and that would cause the scales in this case to tilt. But because we're looking at balanced forces, we need to try and balance what is going on the other side of the scales, and to do that we would put a 1 kilogram mass on the opposite side of the scales, and again gravity is going to be pulling that mass down with a force of about 10 newtons. So what is actually happening with these two forces is, even though they're both downwards, they're acting on this part of the scale in opposite ways. The mass on this side is trying to pull this side of the scale down, whereas the mass on this side is trying to pull this side of the scale up. And when we look at these two arrows, we can see that the forces are acting in opposite directions on the lever part of the scale. So in this case we would say that the forces, both 10 newtons but acting in opposite ways, are what we call balanced forces. We'll look at a person standing on the ground. We know that gravity is acting on that person, so the force of gravity will be acting downwards, and let's say in this case it's a force of 750 newtons. We also know that the ground is pushing up on the person, and that would also be a force of 750 newtons. So when we look at that, what we need to do to work out the motion of this person is to work out the net force that is acting on the person. So again, it's a sum of the two forces acting, 750 newtons down plus 750 newtons up. And again, when we look at that direction, we can see that these directions are opposite. So these two forces are counteracting each other, which then gives us an overall net force of 0 newtons on the person. And because the person was initially stationary, it means that this person is going to remain stationary. There is no net force that is going to change the motion of this person. Let's look at a slightly more complex situation. We have an aircraft that is flying level at a certain speed. Now, there are more than two forces acting on this object. We know that because the aircraft has mass, there must be a downwards force due to gravity. We know that to remain aloft, there must be a force that balances that out, and that is the force of lift. Because the plane is moving through air, we'll just turn that off, that there must be a force due to friction acting to try and stop the aircraft from moving, but the aircraft needs to keep moving, so the engines of the aircraft provide a forwards force called thrust. So we have four main forces that are acting on the aircraft while it is in flight. We need to work out the net force that is acting on the plane, and that is the sum of all of the forces acting on the plane. And once we know that net force, we know what is going to happen to the motion of that plane. So we look at the plane again. Let's start assigning some numerical values to those forces. The force of gravity acting downwards will assign a value of 3 million newtons, and that would correspond to an aircraft mass of about 300,000 kilograms or 300 tons, and that is about average for a large commercial airliner when it's in flight. To balance that force of gravity, we'll say that there is a lift force also of 3 million newtons. We'll say in this case that there is a frictional force trying to slow the aircraft down of about 1 million newtons, and to counteract that frictional force, we'll say that the engines are providing a thrust or a forwards force of also about 1 million newtons. Now we have four forces here acting in four different directions. It's easiest to break this situation up into vertical, and the vertical forces are these two forces, and worry about them first, and then once we've calculated the vertical forces, then we'll look at the two horizontal forces. So we're looking here at two different problems. So we'll start with the vertical forces. We have 3 million newtons due to gravity down, 3 million newtons due to lift up. So we'll calculate the net vertical force on the aircraft. It is the sum of those two forces. Now you'll notice that rather than writing 3 million, I've used kilonewtons, where kilo equals 1,000. So a kilometer is 1,000 meters. A kilogram is 1,000 grams. Kilonewton is 1,000 newtons. So when I say 3,000 kilonewtons, I'm actually meaning 3,000 thousand newtons, and 3,000 is 3 million. So we have a force of 3,000 kilonewtons up and 3,000 kilonewtons down. Again, what is most important here is to look at these directions. They're opposite directions. So these two forces are opposing each other in the effect that they have on the aircraft. And that gives us a net vertical force of 0 newtons, which means that the vertical forces are balanced. So the vertical motion of the plane is not going to change. So if it was traveling level in flight, then it's going to continue to do so. We now need to look at the horizontal forces. So we have 1 million newtons towards the left, which is opposing the motion of the aircraft, 1 million newtons to the right, which is our thrust force. So we need to work out the net horizontal force, which is the sum of those two forces. Note again the opposite directions, which gives us a net horizontal force of 0 newtons. And that means that the horizontal forces are balanced, so whatever speed the aircraft was travelling at, it will continue to travel at that speed, so long as those two forces are balanced. So when we look at all four forces together, we have 0 newtons in the vertical direction, 0 newtons in the horizontal direction, which gives us a net force on the entire aircraft of 0 newtons. And that means, of course, that the plane cannot change its state of motion, which means it will continue to move through the air at a constant speed. That's a vertical speed and a horizontal speed until something changes, and that could be the pilots increasing the thrust, decreasing the thrust, angling the plane to go up or down. We'll look at one more situation to try and understand balanced forces. We have a person riding a bike, and in this case we know that there's gravity acting, and we'll say that that is 500 newtons down. We know that the ground is pushing up with a force of 500 newtons. We'll say that the friction that is acting on this person on their bike is 750 newtons, and when a person is riding a bike, to maintain a constant speed they need to continue pedaling, and by continuing to pedal they're providing a forwards force, and we'll say that is also 750 newtons. So like we did with the plane, we need to actually start calculating the forces in the vertical direction and the horizontal direction. We'll start with the vertical. So the net vertical force equals 500 newtons down, and it's fine to use an arrow instead of writing down, plus 500 newtons up. Opposite direction, same magnitude of force. We get a net force in the vertical direction here of 0 newtons. So those two forces are acting to oppose each other. We look at the forces in the horizontal direction. Again, we'll do a calculation. So the net force here equals 750 newtons to the left plus 750 newtons to the right. Same magnitude of force, opposite direction. We get a net force of 0 newtons. And when we combine both of those results, we see that the net force on the bike is actually going to equal 0 newtons, which means that the bicycle and the rider will not change their state of motion. So whatever speed the bicycle and rider were traveling at, they will continue to travel at that speed. They won't move up into the air, they won't fall through the ground. Their motion will remain constant.